All right, so I'm going to continue now discussing lattice systems in some, okay, let's see. Okay, there's Chuck. Okay. Yeah, thanks. Yeah. So lattice systems. So we have this algebra A, C-star algebra, and inside it, which is a completion of some algebra of local observables, which is just an infinite tensor product of some matrix algebras. And we're going to be trying to understand how to extract some numerical invariants of pure states on this algebra, which is called omega. So it's pure state. And there's some also time evolution, but it won't play a role for now. Some family of automorphisms, well, one parameter group of automorphisms of A, but it's a very special one, so we'll discuss it later. So first thing I want to do is physically, you almost never deal with some arbitrary elements in this A. So really, the interesting observables are either local or approximately local. So I want to define a very convenient class of almost local observables, which is some dense subalgebra of this A. And it's defined, well, we can, for example, define like this. Let's define some, first of all, measure of localization. Like for any, like A in this quasi-local algebra, let's define some function. Well, let's also fix some site. And let's define some function which tells you how well localized, how well this A is localized around point J. So here we're going to try to approximate this A. Well, different ways to do it, but one way is to say, well, I want to approximate A by B, which is a local observable. I also, in the future, I'll call, for any X subset of my lattice, I'll say, I'll define this. Well, say finite subset, define this thing. And then I'm going to approximate my A by local observables, which live in a ball of radius r with center J. So that's well, really intersection. With abusing it, intersection of this ball with my Euclidean lattice. Okay. Okay. And of course, this function goes to 0 as r goes to infinity, but I'm going to demand, so it's a set of all this A such that, well, in this quasi-local algebra, such that this supremum is less than infinity for some particular J. So it just means that your accuracy of approximation, sorry, for any alpha, yeah. Okay. J is fixed. J is fixed.
Wait, but then this almost local depends on the choice of J.
Actually, it doesn't, because the number of points in a ball grows only polynomially. And here, essentially, required that my accuracy approximation is better. No, it gets better and better very fast, faster than a polynomial. Actually, it doesn't matter what choice of J. It's the same subset. Okay. So now another way to say it, you can say, well, it's a completion. Also, so you can also say. So AAL, almost local, is a completion of local observables with respect to a countable family of norms. Well, semi-norm. Well, these are already norms, by the way. So every guy here, you can call it like norm A J alpha. So it actually is a norm, not just a semi-norm, but you can say it's kind of also family of semi-norms or norms. Namely, well, you can say first of all, what is this norm? This is this guy, and then all these other ones. Just element of this finite, well, just this product. Just the element there is always a element of some finite, it's just a direct limit. Or all, well, just an element here just has almost all ones except finite number. So just a big matrix. So so we have this. And because of this, this guy is actually a Frechet space. So it's actually Frechet algebra. Okay. So and it's very convenient to work with. Now in practice, I usually mostly work with sort of traceless matrices, if you wish. So you can define the notion of a trace even for this quasi-local one. So I remove sort of identity. So the identity has a problem. It's sort of localized everywhere, but everything else can be sort of what's everything else? It's better to sort of restrict to traceless observable, and then it's easier because also then if we call this guy say is the subspace of let's say actually anti-self-adjointing traces. Observables, then this family of semi-norms is equivalent to sort of, maybe call this prime. Okay. It's easier to just define. For those, you can just, it's equivalent family of semi-norms like this. It's just and now alpha is a 1.
So this can I think of local as compactly supported function, almost local as smooth.
Yeah.
This GAL is
Well, smooth, I wouldn't say smooth. Decaying, like Schwartz type stuff. Decays faster than the power. So, yeah, and these are like just some very moderate decay, which is that's a kind of useless thing because, for our purposes, because the rate of decay of tails, like how local, is not constrained at all, basically. So it's not convenient to work with. Okay, so that's the base. This guy is actually one of the main objects to work with. It's actually a Lie algebra, a real Lie algebra, but Frechet-Lie algebra. But we're not gonna. Well, I'm going to return to this structure later. Now, as sorry,
the A without subscripts is operators with any decay at the support.
A without subscripts.
Is that algebra A?
Yeah, this is just C-star algebra. So just completion with respect to the norm, just single norm. So it's a Banach space. And yeah, I'm almost never work with this guy. I always work with this almost local or this subspace. Okay, the next thing is we want to define some nice class of derivations, that is Hamiltonians, roughly speaking, which preserve the subspace. And one requirement, you want to be able to exponentiate this derivation, so actually get time evolutions easily. So here is it's not the most optimal definition, but it's the shortest one. So a uniformly almost local derivation, or can you say nice derivation, is a derivation of the form, so let's call it where okay, maybe I should have some other terminology. So we'd say that so if you have some if you have any particular almost local observable, so you can define this function f of j of r. So and if you have if you say that, if your fj of r a r less or equal than same h of r, where this is decays faster than e power, then you say that a is, well, not kind of approximately localized, but I don't want to overuse the word localized. Let's say a is h confined at j. Okay. So just to have terminology. So when so I'm going to say that derivation of this form is a UAL uniformly almost local derivation. It has this form where f of j is h confined, or f confined. No, that's it. So h confined at j.
This fj is not the same as the course.
So the j here is, well, each of these guys is confined on its own site. Okay, so so here you can, in the definition, it doesn't matter what j is because you just get different.
I'm just saying that there are two fj's now and they have nothing to do with each other.
Yeah, that's bad. So let's not do this. Let's do let's do this kind of f. Okay. So this is going to be derivation of this form is going to be called uniformly almost local. These guys are actually not even here. They're like here. The traceless or self-adjoint, and it does, doesn't matter because one would drop on anyway. The scalar would drop out. That's so just convenient to fix this ambiguity, and also it's anti-self-adjoint because I want this derivation to preserve self-adjoint elements. Okay, so I mean, in other words, because of what I did, I have this property. Okay. So now that's not the best definition of these nice derivations because there are many different choices of this curly fj which give you the same derivation, and that's an important point that there's ambiguity there. So
h is for some h.
Sorry, for some fixed h, which is for some positive function h of r, which is decays faster than e power.
Ah, I see. So that's the uniform.
Yeah, that's uniform. So almost local, but also each of these guys is bounded by the same function. It's confined in the same way. Okay. Okay. So now this ambiguity is a kind of an important part of the story. Okay, I forgot to say that that's also, you can also think of this, let me call this space of almost local, these guys, the space of UAL derivations. Of this almost local algebra or the subspace. It's easy to check that it preserves almost locality of an observable. So it's so actually it's a Lie algebra, and it's a Lie algebra. It's a Frechet-Lie algebra. And you can similarly to this almost local observables, you can define some nice natural family of norms and say it's completion of some, say, finite range Hamiltonians or derivations with respect to those norms. So it's a similar thing. So that's of course the most important thing about this derivation is that they can be exponentiated. You can actually time evolution. Any derivation from here can be exponential to actual time evolution, and that's consequence of some important theorem called Lieb-Robinson bound. But I'll get to that later. But also an important thing that a nice thing is that all these guys have common dense domain of definition. This one, and you can take commutator, you get this object of the same kind. So it's a nice Lie algebra. Unlike just it's unbounded in the sense of this big algebra curly A, but it's nice as far as this almost local thing is. And physically, they just correspond to interaction. These derivations correspond to interactions which decay faster than e power. And that's very convenient. Like say finite range would be one of those. but finite range turns out to be not big enough for all purposes. So now it's important now to discuss ambiguities in this choice of these things, and that's really the crucial part of the discussion. So what are the ambiguities? Well, there's let me discuss first ambiguities, analogous ambiguities in field theory. So ambiguities in say densities and currents in quantum field theory or classical field theory, whatever, either. Just as a motivation for what to follow, so we have something to connect to. So in field theory, you typically, suppose we deal with some symmetry of the theory that corresponds to some derivation on the observables, and typically write this derivation as an integral of some local thing called density in these spatial dimensions. And then there is some local of course Q is conserved, but also some local conservation for density. So it's called density of safe charge. And there is a conservation of density, which people usually write this way, where J is current, but sort of some sort of vector field. But I prefer to and I prefer to think that rho is not a function, but rather a capital D form. So and then it's natural to think of this J not as a vector field, but as D-1 form. So I'll just write it this way. So rho is a D form on our manifold, well, times R, because that depends on time, and J is a D-1 form. Okay. And then there are various ambiguities here. For example, rho itself is ambiguous because you replace rho by rho plus d of something. Let's say k does not changes q only by sort of boundary terms, by surface terms. And in particular, doesn't affect the symmetry transformation for which this is a generator. So similarly, well, of course, if you shift rho like this, you have to solve J by K dot or something, right? So similar thing.
So what's written there? So minus D sub J?
This is dj. J is a D-1 form. Okay. So if you do this, you of course have to redefine J as well, shifted by minus K dot. But also, so it's one ambiguity, but there's a second one. Even if for some reason you have a fixed rho, you still have ambiguity. You can shift J by J plus dm, where m is some D-2 form, well, observable with values in D-2 form. So that's also a standard thing in field theory. All currents, all densities and currents are always ambiguous. And that's not a big problem, it doesn't change any physics, but it's important to keep this in mind. And similar thing happens on the lattice, so let's discuss those. So what's the analog? On the lattice, suppose I lattice ambiguities. And what's the first analog of charge? Well, the charge is our derivation. So instead of writing f, I'll write have some derivation which is called q, and it acts by assumption. It acts like this. So roughly speaking, q is a sort of formal, big q is the sort of formal sum of these qj's. Now, so instead of density, you just have a collection of this almost local observable, one for each side. So that's an analog of this rho. Now, what's the ambiguity here? Well, there's one obvious one. You can do that, where should put capital K. So where where this Kij, well, what is it? Well, for this to make sense, for this shifted guy to be of this, first of all, for the sum to converge, and for the shifted guy to be of the same kind, you want to say that first of all that Kij, well, is, well, first of all, this condition ensures that this derivation doesn't change. That's the condition which ensures that the derivation doesn't change. Then second, you want the sum to converge, so you want these guys to, well, okay, so also use it only for duration, so it's still Kij is also in this traceless self-adjoint almost local observables. And third is confined, well, say H confined, not F confined at I and J. So it's almost local observable, which is localized both on I and on J. So of course, if something is localized both here and there, and these two things are far from each other, there's no way to do that unless this thing is small itself. So that ensures a very rapid decay also of this Kij, faster than any power in norm. So as a result, this sum is very rapidly convergent, so there's no issue of convergence. So okay, so that's ambiguity and the charge density for a given sort of net charge, given derivation.
F needs to be like bounded by this H you had before?
See?
This F needs to be bounded by this H you had before? Like Kij is F.
Well, F is just whatever. So if this thing was H confined, then, and this is some F confined, then this new one is confined with respect to some other function, the max of the two, so it doesn't matter. So it's still a well-defined guy from the same vector space. Okay, and here there's an analogous thing. So if you fix already your Q's, okay, first of all, what's the analog of this equation? So the analog of this equation, local conservation equation in the lattice is looks like this. We'll just write something like this. So, and here Gij is a kind of similar object to this fella, which was ambiguity in the charge density. So this guy, where Gij is Q-symmetric. Well, it's Q-symmetric now for a different reason. It's Q-symmetric because the interpretation of this thing is the flow of charge from point I to point J. Sorry, from J to I. From J to I. So
this Gij is the commutator of Qi with Qj?
No, it's just a flow. It's just saying what would it mean to have local conservation. I mean,
say that this equation is produced by applying derivation and viewing it.
I'll write it down explicitly. But just saying, suppose a priori I wanted to have some notion of conservation in the lattice. What would I say? Because this equation is very general, right? For example, this equation holds not even in field theory, but in some dissipative case or without any Hamiltonian evolution. It's just a statement that for something to change, it must come from somewhere else, right? So similarly here, you could say, well, what does it mean for local conservation? It means that if something, as Lomonosov said it, if the amount of something at side j increases, then it must have come from some other side I, right? So there's a great Russian scientist, Lomonosov, from 18th century, who figured it out. And he probably would write something like this, right? So, because this is the flow of stuff from I to j. Well, sorry, that way, from j to I. And the flow of stuff from I to j must be the opposite of that. So that's why this Q-symmetry. That's just, by definition, essentially what flow means. And since Q was traces self-adjoint and anti-self-adjoint, the same must be, well, probably true here, and should be also localized, right? So it must be almost local. And also, if something flows from side j to side I, or the other way around, it must have been some quantity which is localized on I and j. So it's the same thing then. Is f confined for some other f at I and j. Okay. So that's conservation law on the lattice. And clearly there's ambiguity here too. Like even if you fix this side, there's ambiguity here, which let me write here. Where M is some object with 3 indices and similar properties. It's completely symmetric in all 3 indices. So by the way, for some reason, condensed matter books never discuss how to define conserved quantities or currents or on the lattice, but it would make everybody's life easier if they did write something like this. I learned about this sort of formalism from Kitaev's, on Kitaev's paper, this anyons and integrally resolved model. It makes things much easier. So you can, for example,
So what is the relation between Q and J? So far, no relation. Oh, sorry.
I'm just saying that, okay, so for any particular theory where you expect local conservation, you expect something like this to hold, right? Now you can, if you're in a situation where you, okay, if you're in a situation where the evolution is Hamiltonian, right? You should be able to massage your equation of motion or Heisenberg equation of motion to this form for the conserved quantity. For example, let's get an example. So suppose you're interested in energy itself. Suppose Qj is the density of energy itself. In the sense that H is sort of a formal sum of these guys. This is the Hamiltonian. So it's a UAL derivation, but I write it as a formal sum, just shorter. So can we massage the conservation of local conservation of energy into this form? Well, we have Heisenberg equation of motion. So you see that's has the right form pretty obviously, right? So in this case, I would say that the energy current could be chosen to be this. Okay. So and similarly, you can check for electric current what you get there. So again, this solution is not unique, but it's kind of in some sense canonical once you specified what your density of energy is. Okay, so again, there's always this ambiguity to add something like that. Now the next question is, okay, what are these all this? Are these the only ambiguity? That's another thing. You define all of them. Like in the continuum case, we have Stokes' theorem, which tells us actually yes, that's or Poincare lemma, if you wish. It's more of Poincare lemma, which tells you that actually these are the only ambiguities. But on the lattice, we need something similar. So let's see. What I can say there. So okay, so to formalize things, well, we have it's good to introduce this object. So an n chain. I'm not going to say like in what with values in what, just an n chain is a collection of observables. Well, is a function from. Well, let's just call it. So for now on, let me just say that shorthand. This hypercubic lattice is called lambda, and actually in the reality you don't have to work with this lattice. You can take any Delaunay subset of Euclidean space. There's some subset which is like doesn't have accumulation points and doesn't have very big holes. In the theory works the same way. So a function from lambda times lambda n times to this almost local, well, this traceless anti-self-adjoint almost local observables. So J1, Jn maps to say F J1, Jn such that, well, first of all, you have skew symmetry. know its indices. Then and then this is say H confined at J1 Jn with the same H. Okay. So as a consequence of this, this object decays rapidly, faster than the power of if any of these 2 points become far from each other, because it cannot get localized at the same, 2 points which are far apart unless you're like small. So so motivation, of course, is that our charge density, so our say density of charge. Okay, so the space of n chains, call it Cn. And the motivation is that our charge density lives in C1 and our current lives in C2 and so forth. And you can just say that, so n here is 1, 2, so forth. And let's just denote the set of this nice derivation as C0. Just to define it. And the reason is because somehow almost local derivation is like a formal sum of density over all sides. So it's so you can actually include all these things into a complex. So we get chain complex. Sorry? Yeah, at first in our paper with Nikita, we call this n plus n minus 1 chain. So we have n indices by analogy, like with
but then C0 is
has no indices.
okay.
So now before we're like, okay, it's like check complex. So have one index, like for cover index, we'd call it 0 chain. If it has 2 indices, it will be 1 chain. But as we'll see in a second, it's actually not very convenient convention. It's better to, first of all, because this guy would then occur in degree -1, which you don't want. And second, because actually these guys also have additional algebraic structure, which is, and it's not optimal to label like that. But, so anyway, so we have a chain complex, and for the way it works is simply summation, just like in the check complex. So. Summation of the first index. So that clearly squares to 0 because all these guys are skew-symmetric. Okay, for the n equals 1, it's a bit different, of course. For when you act on a 1 chain, so that's for if f is in Cn and greater than 1. Like if we have n is 0, then it's a bit different. Then there's also a derivation. So if f is in C0, then now del f, the derivation given by which acts on observable like this. But it's really the same thing. Takes sort of a formal sum, if you wish. It's well defined though as a derivation. Okay, so so far what I said, that they have these ambiguities in the definition of, say, density. Well, say derivation is ambiguous up to the image of this del, just means these guys actually form a complex. Now the next question is, what are all the ambiguities? Well, are there any other ambiguities besides the one I described? And there's a little theorem. So this complex is acyclic. So no homology, which means there are no non-obvious ambiguities. Okay, so that's not very difficult to prove. I won't do that. Now okay, so far so good. Now another way to say it, well, you can think of this whole thing as a resolution of this object here in some sense. And that's a Lie algebra. So on general ground, you'd expect on this piece to have maybe L infinity structure, something like that. Okay, you would like to say, well, maybe you can leave this bracket, which you have here, to brackets between all these other guys. But when this bracket might only satisfy Jacobi up, or maybe you can Q-symmetrize it if you wish, but there's no guarantee it's going to satisfy Jacobi. Maybe it's going to be Jacobi up to some del of something else and so forth. So you can get some complicated things. Luckily, it doesn't happen here. As far as I know, well, this is where the analogy with field theory actually, I think, breaks down. In field theory, in general, you do get some weird stuff when you start working with densities, but in lattice, you don't. And because in reality, there's another structure here, which is much simpler than L infinity or whatever structure. The whole thing is turned out to be just a differential graded Lie algebra. You can sort of extend just usual Lie algebra structure here to differential graded Lie algebra on the whole thing. So let's define. Bracket. So let's say I will just denote the C. So claim is a differential graded Lie algebra. Well, it's actually Frechet-Lie algebra. It's all these spaces of chains actually Frechet spaces. So, and all these brackets are continuous. So how is it defined? Well, the most kind of naive way possible. We already know. Well, if you one of your okay. So how do you define, say, f and say f prime, and say this is lives in Cn and this lives in, say, Cm. Well, there should be an n plus m chain. And that's, by the way, why I graded the way I did, because before in the paper, our grading is shifted, so the result, the degree is shifted by 1. The degree of the bracket is not just n plus n, but it's shifted by 1. But we realized too late that it's not a good convention, so I'm here in the good convention, and this guy is going to be n plus m chain, and its components up to some numerical factor, which is basically your convention, is numerical factor is just this. So just Q-symmetrize. Okay, and it turns out that, okay, so it's you have some, when I say graded Lie algebra, it well just means that it's graded skew-symmetric. So for example, the usual derivations are bosonic objects, so they form a normal Lie algebra, but say chains, which are densities for derivation, actually kind of like fermionic. So their bracket is symmetric rather than skew-symmetric and so forth. So you can actually see it, right? So say if you look at, for example, for bracket of, say, suppose n equals m equals 0, right? Then this bracket is going to be actually symmetric and f and f prime. So, okay, and on top of that, you have a graded Leibniz identity. So that's the part, the differential graded Lie algebra. So say f prime is going to be
Didn't you consider the case n equal m equal 1 there?
sorry, yeah, I slipped to my convention of the paper, which is the wrong one.
You also did it earlier with f in C0.
Yeah.
That's
No, C0 is fine.
no.
No, it's also no, it's wrong too. I slipped again. So, okay. Yeah. Okay. So when you pull like del through f, if it's a fermion, you get an extra minus sign. That's graded. That's the usual graded Leibniz. Okay, so So this structure is actually quite useful, although not for the time being. Although, well, it allows you, for example, to express various currents in sort of index-free notation, if you wish. Say, I just erased this thing here, so I just wrote that the energy current is minus commutator of this energy densities, but you can also write it in index-free notation. No. The energy current is a 2-chain, which is just this. Okay. So, and similarly for the electric current, you'll find that, so this is energy current. And similarly for the electric current, you can find it's actually equal to the, say if you have some charge Q, which is like formal sum of these QJs, then the electric current is minus H Q, where H is the density corresponding to energy, and this is the density corresponding to charge. So you can sort of write everything in terms of, without putting indices. Okay, so this part is relatively trivial. Now here comes, now more interesting things happen when you, okay, so these were just sort of kinematic, if you wish, considerations. Now finally we get to the interesting part, namely suppose omega is a state. For now, just arbitrary state. And then we want to define now symmetries of this state. So usually in physics, when we talk about symmetries, I mean something which preserves the Hamiltonian. But I already said that Hamiltonian is not terribly important. So we're just going to work with states. So we need to define symmetry just knowing this state. And for me, symmetry is going to be something which does not excite the state. Like in the quantum mechanics, it would mean like if I have some operator when it acts on my vector in the Hilbert space, then it actually, the vector is an eigenstate of that operator. That's what I mean by does not excite the state. Say, for example, if it's a unitary guy, it just multiplies my vector by some complex number with absolute value 1. So that's what I mean. Okay, so but we want to say it in an infinite volume. So we say make the following definition. Say first for derivations. So if some f does not excite omega, if have this. So in Hilbert space notation, it would be like something like, in Hilbert space, you would have if you use this Gelfand-Nymark-Siegel construction, you can associate to A an operator in Hilbert space. Omega would be a vector state, so you'd have some vacuum vector, which represents omega. The average in omega means just taking average in some vector space, and you would say something like this. You have some Hamiltonian corresponding to F, and this would be something like this. So that's literally a state condition that would say that, so if F was say some charge, right? You would say that this is the condition, which means that there's no spontaneous symmetry breaking. That your ground state is actually eigenstate of your, well, annihilated by the charge roughly. So, but I prefer to work with the C-star language. It's just easier for most purposes. Okay. As I mentioned, by the way, you can also exponentiate arbitrary element here to some actual evolution. After exponentiation, this condition means that your state is invariant under the one-parameter group of automorphisms, which exponential this derivation gives you. Okay, so that's basically a symmetry of a state, very natural notion. Now here's a less natural notion, some strange-looking notion. Well, since we define it for derivations, and derivations same as zero chains, let's define also for n chains. So now that's a less natural thing. If you think about this, let's look at the case of, say, n equals 1. So n equals 1. So in that case, what does it mean? Well, it's going to require, say, suppose our derivation is some charge density. It's called Qj. Well, in Hilbert space language, it means that every single local density, local charge is actually has ground state as its eigenstate. That almost never happens. Like if you like, that's almost never. It seems like it's a useless notion. But actually, that's not true, as we'll see. And surprisingly, there are lots of such chains which do not excite the ground state. That's actually an important part. The most important part about this. But anyway, the point is that if you start with suppose Q is our, say, charge does not excite, and Q is a formal sum of its charge densities. Does not excite omega. So can one choose Qj using the fact that this is a one chain, this is a zero chain. There's ambiguity, lots of ambiguity. So we have Q is del Q. Can you use ambiguity in Q by adding something exact to it to make it so that this can you choose Qj so that Qj does not excite. So this guy does not excite omega. Okay. So let me just.
So can you say again what this parenthesis on the subline? What does it mean?
Parenthesis. Not parenthesis, quotation marks.
Quotation mark.
It just means this. In detail, I would say that you should really write in terms of commutators with some. So I would say that the action of Q on some local observable is the same as this. So I just use a shorthand. So because in some sense, this is a formal sum. Okay. Let me postpone it for a few minutes. This question. Okay. Let me just formalize a little bit this objects we just defined. So so we have this. Of course, this guy sits inside all chains, but moreover, it's a subcomplex. So it's quite clear, like if you sum over one index, it's still gonna satisfy the same conditions. So, so C and omega del is a subcomplex of guy. And in fact, it's also the bracket actually is close to the bracket. So in fact, it says it is a sub-differential graded Lie algebra, which is direct consequence of Jacobi identity, the usual Jacobi identity. Okay. So so the question let's go back to that question. So I have this sub Lie algebra with differential, and forget for a second about Lie algebra structure. We want to ask whether one can lift, say, any. So suppose you have some. Well, let's start with this guy. Say suppose a Q lives here, and suppose it lives actually here, and you want to lift it here, right? So you want to. There's a question of whether what's the homology of this complex? Are there any things which are cannot be like lifted to, which are closed, which are cycles, but are not boundaries in this complex. So at first sight, like it seems like, well, it's probably not going to happen because, as I said, it seems physically, it seems very rare, say, to have, say, one chain which does not excite our state, say, which is our ground state of Hamiltonian. Well, for now, omega is arbitrary, but now let's specialize with the case when omega is a pure state, and moreover, it's actually unique ground state of a gapped Hamiltonian. So, so I want to ask, is it true that maybe in this special case that this complex is still exact, so you can still lift every, say, derivation which doesn't excite the state to some one chain which does not excite the state, and that turns out to be true. If omega is a unique gapped ground state of some uniformly almost local Hamiltonian. Okay. That's not only a non-trivial step, really. So the special case of this was shown by Kitaev, and Kitaev showed in the special case when the derivation I was talking about was actually Hamiltonian itself. So if you have some Hamiltonian, of course Hamiltonian does not excite the ground state by definition. So you have this condition, right? Obviously, simply because it's it's an eigenstate. By definition, the ground state is an eigenstate of Hamiltonian. And the question is, can you write H as a sum of terms, call them H tilde, so a formal sum, where these guys are maybe different from the original ones, but so that they sum up to they give the same derivation, but so that they do not excite, but so that you have so that the ground state is an eigenstate under each local term. So in other words, this is satisfied. So Kitaev showed that's the case for Hamiltonian, and his arguments can be generalized to arbitrary derivations which do not excite the state, and in fact they can be generalized to arbitrary chains with the help of that other theorem about the acyclicity of the the same complex without omega. You can extend it to this the whole thing. Okay. So this is the most important fact, and that's the only place really, for now, where the condition of being gapped enters into the theory. And so maybe, by the way, one thing, I just want to take a break maybe now, but let me just say that this fact is actually, or its generalization of this to the case of arbitrary derivations is actually very nice fact, which allows you to give you like a one-line proof, say, of Goldstone Theorem. So once a trivial application, so Goldstone Theorem. So the way usually physicists state it is saying that, well, if you have some symmetry, if you have some symmetry of the Hamiltonian, and if you have a ground state which is not invariant under this symmetry, then you cannot have energy gap in the spectrum. So let's prove the contrapositive. Let's show that if there is a gap, then the symmetry, then your charge cannot excite the ground state. So how do we do this? Well, we use this fact. So suppose you have your charge as a formal sum of local charges, and I know that I can also modify. I can say that I can define new charges by adding to this old charge density something exact. So in such a way, so there's some choice of this guy such that the average of this new charge density is 0. So that's what exactness means at n equals 0. So I can adjust my choice of charge density so that this is satisfied. And this guy is still going to be almost local. Like originally you start with a charge, typically, where each of these terms is just local observable on one side. But turns out you can add something, spread it out a little bit, and then you can make sure that every local piece still doesn't excite the ground state.
And what do we know about the action of big Q on the ground state?
So of course, we want to show, that. So we want to show. Sorry. No, wait. Sorry. No, sorry. Okay, sorry. That's not right. How do I do this? Okay. Let's see. No, it should yeah, sorry, Q shouldn't be, yeah, Q is doesn't. Okay. No, wait, sorry, it's not related to this fact. It's somewhat related. You know, let's scratch that. It's a related argument, but not exactly the same one which shows Goldstone Theorem. Anyway, so okay, I won't show how to prove this. It's just some fairly standard trick, which no, I just won't do this. So it takes too long. So and the second half of the talk, I'll apply this fact to define invariance, well, the whole conductance and the general invariance of system with some Lie group symmetries and also these higher Berry classes for families of symmetries. Okay, so now we get to the interesting part, if you wish, namely how to use this technology to define some sort of numerical invariance of states. And by invariance, I mean some invariants which do not change under some notional equivalence of states, or gapped states, and therefore can be thought of as numbers assigned to phases. So these phases are like so. So that would be ideal. Unfortunately, so far we didn't find any non-trivial invariants which can just assign to a state. So without any further being gapped and no further structure. So the prediction is that such invariants should appear first in dimension 2, actually. So I displayed some table expectation from this refined Kitaev conjecture, saying that at least for invertible states, you expect some integer-valued classification of phases in 2 dimensions. So in dimension 1, there is nothing. Also, well, there's nothing for just the space of states is connected in dimension 1. It has some interesting topology. We'll get back to that, but it's connected. Now, right, for 2 dimensions, also you can consider more general gap state, non-invertible. In that case, we expect lots of actually disconnected pieces. But again, I don't know. This technology doesn't help you to yet, at least, to zero in on any one of them. And so instead, I'm going to do something easier, namely invariance of states with symmetries. Okay. So you can define. Okay, so we can assign numerical invariance to states with symmetries. Of gapped states, gapped ground states, with symmetries. And what I mean by this is that, well, not just the state is symmetric, but also the Hamiltonian. Well, I know that that is omega is a unique gapped ground state of some UAL derivation, called the Hamiltonian, called H. And in addition, okay. Like in addition, Lie group G acts on on my algebra, on each local algebra observable. That's how it is usually in physics. So that and the action commutes with each ij and preserves omega. Actually, the last part not important because there is Goldstone theorem, which I'm going to explain, which ensures that it's actually the case. If you have a gap, then you cannot have non-invariant ground state anyway. But so why each it seems like a bit unnatural to require each ij to be invariant. Well, it's actually not an important constraint. I guess I'm doing a compactly group anyway, because it acts on these matrix algebras, right, by unitary by automorphisms, star algebras. And if it's compact, well, even if you're unfortunate, you maybe made some unfortunate choice of these local densities, which are not separately invariant. You can always average them over the action of the group, and you're going to get some other Hamiltonian for which they're invariant. So it's actually not a constraint. So since we don't care about particular Hamiltonian anyway, and also if you average, actually you preserve the whole thing. Right? You can average over the group, and the formal sum will not change because by assumption the whole thing is invariant. So it's actually not a constraint. You can always assume this. It's just kind of more convenient. The constraint is H, the whole formal sum is invariant. That's an important constraint. But each of them individually will seem strange physically, a little bit strange. Typically, it is like that anyway. So usually when somebody hands you Hamiltonian, says, look, it's U1 invariant, for example. Usually each term is U1 invariant. But sometimes, there are also exceptions, but it's not really an exception. They're not real exceptions. You can always, it's basically a statement related to some statement like this in physics, says there are no anomalies on the lattice. That's basically what it is. Like if you don't have them because you can always change the choice of this H so that each of them is separately invariant. Okay, so supposing this situation. So when I establish, and when we want to assign some numerical invariance, which are going to be unchanged under some natural equivalence, which I'm going to talk about later. So, and let's do a case of U1, for example. The general case is not terribly different. This is also physically interesting because physically that's actually where whole conductance come from. You have conservation of electric charge, so there's U1 symmetry, and we expect the whole conductance to emerge somewhere in from our theory. So, okay, so what do we have? So we have this H, and it's not terribly important what it is. As I said, the important thing is to have this omega. So we have omega. We construct this. Okay, so we have also this charge, which generates a symmetry U1 to some of these local guys. And again, I might assume that all these guys are separately, U1 invariant too, because if they're not, you can just average. And I can look at chains which do not excite my particular state. Called omega, yeah. And also U1 invariant. Okay. So these guys, well, so why? Well, because my H's and my Q's all live in that subcomplex. Now again, you need a separate argument, but it's a trivial extension. The fact that this guy is exact, this complex is exact, easily you can modify the argument showing that this invariant part is also exact. I mean, acyclic, sorry. It's a acyclic complex, and that's simply because you can sort of average again over U1. So let's see how we can use that, this triviality of homology. Okay, so we have this Q, so we can also write this. Since Q does not excite, so Q lives here. Right. So we can therefore find some Q tilde, maybe not the original one, which lives here. Right. So simply by acyclicity. Okay. So that's a guy with an index living on the lattice. And then what's another thing you can do with it? Well, so the original guys, by the way, they all typically chosen so they all commute. But we can ask, okay, what about, so they're all chosen actually. They're all chosen so that they commute because the action is separate on each side. Right? Now we improved our charge in some sense, our charge density, so that it preserves the state, but does it still act on site in some sense? So what about this? In other words, what about this commutator? Is it zero or non-zero? So now, or in the index representation, I would just say it's a bracket of the tilde with itself. Remember, it's fermionic object, so its bracket itself doesn't vanish. Okay. So now what can I say about it? Well, we can hit this left-hand side with del. So if you hit with del, so we're going to get Q. And I remember, so all these guys by assumption live in the invariant part of this complex, so that's 0. Right. So by exactness, you can find then this guy is closed, therefore it's exact. So you guaranteed that there's some. So this guy is a 2-chain because 2 indices. So there's some 3-chain called M, or maybe we should call it something else, but anyway, it's called M for now. M lives in C3, and I can choose it to be preserving the state and U1 invariant. Okay. So what am I going to do with that? Well, first of all, what it is, it's in some sense an abstraction to making, to making this guys on site in a sense, because they actually they don't commute really in general. Okay, but we want some numerical invariant, because this thing, of course, is highly ambiguous.
So I'm confused. So I and J are sites on the lattice?
Yeah.
How can they not commute if they are supported on different sites?
So these guys were supported on different sites. But after I improved them so that the thing actually lives here, they only approximately localized on each side.
This is a Q tilde I does not live on I.
No, it's just approximately, like I said, confined to I. Okay. So how to extract something out of this rather ambiguous quantity? Well, so here, this is a 3-chain. And, well, all these chains, by the way, are kind of lattice analogs of forms in field theory. So this thing I can, so if I talk about forms, it should be some integration procedure. So it should be similar for chains. So how can we integrate, say, 3-chain or any chain? Well, so here that's where the dimension comes in. So D chains can be integrated to, so this integral maps your CD to just a local observable. Okay, but this integration is not unique. There's some, integrate along some cocycle if you wish. So what about an analog of cocycle? Well, in why D chains? Okay, so here there is the following. You have say in 1 dimension, so let's D equals 1. It's very, very intuitive, because in higher D it's not very intuitive. For equals 1, you're dealing with D plus 1 chains. Again, I'm relapsed to my previous convention. Suppose you have a D equals 1, then you should be able to integrate 2 chains, so what's called a current. Well, when you have a 1-dimensional lattice, infinite lattice, one thing you can do is just compute the flow of, say, charge from, say, left half of the chain to the right half. And where left and right is, of course, it's something you need to choose. So, so you can sort of define the integral of, say current over this choice of decomposition of your guy as a simply flow. Okay. So now it's in d equals 2. If you think about this, well, you need to integrate a 3-chain. Well, in d equals 2, you need to choose a decomposition of your lattice into 3 regions, say A, B, and C. And you integrate over, you need to choose the 3 regions and define this some to go 3-chain as something like that. So these things are convergent because this object will decay very rapidly when the indices are far from each other. Say, it's basically localized to this point. Okay. Plus tails, which rapidly converge. Okay. Okay. Of course, there's a lot of ambiguity how you choose these regions. So there's nothing. So actually, I don't even know precisely what's the most general sort of integration region, which is given by this really d+1 regions. So for my purpose, it's sufficient to just choose any region which in infinity look like some sort of conical regions. They're all non-overlapping, and the union covers the whole lattice. So what they do inside is completely irrelevant. They can do like whatever. So the important thing is for them to, at infinity, not to be too wild. Okay. Say for example, we can say that at infinity they are like within some cone of some angle. All these regions. So the property of the integration is the following, that let's see. So property, if del, say, so let f be some d+1 chain, then if it's closed, then integral does not, so L over A1 A d+1 does not depend on the choice of the regions up to orientation. So you can move things around a lot and nothing changes. So now it's kind of obvious in the, it's more intuitive in the case of in one dimension. So being closed means that your charge on the other side doesn't change, right? So if you ask, okay, well, do I get something different if I say put this separating line here? The answer is no, because the net current for any section is the same, because the charge doesn't accumulate anywhere. So the similar thing is also true in all dimensions, but just easier to see in one dimension. So. Now, of course, you could say, well, what's the point of this? Because if if something is closed, we know it's also exact because of this our theorem. So, and you can show that if you have something exact, it actually evaluates its integral is 0, kind of like Stokes' theorem applies. But we're going to use this also for analogous integration exists not just for sort of observable valued chains, which we had, but also numerical chains. So if you have this collection of numbers, which have these decay properties, right? So for numbers, like for our operator valued chains or observable valued chains, we had 3 conditions. They had to be like skew symmetric, they had to be anti-self-adjoint and traceless, and they had some localization property under all these guys. And the last property implied that you have a rapid decay when all the indices are far from each other, when any of the indices are far from each other. If you have instead just a collection of numbers for every set of indices, then you can just suppose skew symmetry and this decay property. And you can still have the same integration procedure, and it's still going to, and that's going to be important, because there, for numerical chains, it's not true that being closed means you're exact. they're actually very easy. You can just take some simple lattice, like say 1D case, just takes 1D, say, and look at, say, chain. So for numerical chains, does not imply that f is exact. So in precisely, because just an easy to invent numerical chain whose integral is non-zero. Just imagine just a, say, a one-dimensional case, which is again easy. Just imagine a numerical chain which just assigns the same number, say, I don't know, 1, to just neighboring sites, and vanishes for all others. Then this clearly, this is a 2-chain, right? So it vanishes for all, say, between here and there, just not vanishing for nearest neighbors. And you can easily check that the flow through any section is 1. So the integral is non-zero. Nevertheless, there's no way to write this as del of something with 3 indices. I mean, because the flow is non-zero. So if you could, then you would get something 0, right? So this thing can be valid to non-zero, but the integral can be non-zero for closed things, which are numerical. Okay.
Was the homology in this case with numerical chains just the usual cohomology of the torus, or?
Well, why torus? Why torus? There's no torus in the problem.
Well, there's a lattice, so there's a torus.
Yeah.
I mean, no. Maybe I'll just ask. What is the?
I actually don't know. Something like this occurs in coarse homology, but the kind of chains they use are a bit different. Like their chains vanish outside of some neighborhood of diagonal. So you have some object with n indices, but the chain is non-zero only within some neighborhood diagonal, some fixed radius, kind of finite range situation. In our case, they can just decay fast. So I don't know actually what the homology is. I'm not sure it's something nice. All I know is that you can get cycles in that homology, whatever it is, from this operator valued guys, which I have. Okay. So let's now see how it works. So, well, it's actually very easy how it works. So we have this M, which satisfies this. So instead, 3 chains, we can just take its integral over these 3 regions, and then take expectation value. It's an observable after all. So explicitly, it just you can also write it in a different order. Okay. So it's a number. Actually, it's purely imaginary because our chains were anti-self adjoint. The claim is that this number doesn't depend on precise choice of these regions. So you can choose them anywhere you want to. It does depend on orientation. If you change orientation, changes sign. So why is that? Well, because so this does not depend on this choice of this A, B, C up to like orientation or up to like cyclic order, because this numerical chain is actually closed. And why is it closed? Well, we just use this, so indeed, so we have del of omega q twiddle. So you get q twiddle. So del m, del omega of m is omega of del m. That's omega of q twiddle. And these guys don't excite the ground. Remember, they form a, this guy is closed under the Lie algebra, right? So, in other words, since this, if you write explicitly, then you're looking at things like this. And so that vanishes because each of these guys don't excite the ground state, right? Okay, so you get this numerical invariant of a state which doesn't depend on any of these choices. Now, of course, there are lots of other things you can choose. You can check that, for example, if I choose a different m, nothing changes. Also, if I choose a different q tilde, nothing changes either. So that's an easy, straightforward check. So that's really an invariant of a state. And it occurs in 2 dimensions. I couldn't get it, say, in 1 dimension because I needed a 3 chain to integrate. Okay, you can ask, okay, what about in which dimension can I get something, right? So so general D. Okay, it's really clear what the pattern is. Let's just go one more step. So, okay, suppose I'm not in 2 dimensions. Someone means some higher dimension. Can I get something? Well, to get some invariant using this construction, I need some d+1 chain. So how would I get that from? Suppose I'm in, say, 3 dimensions. Well, I need a 4 chain. So how can I get it? Well, there's no obvious choice of a 4 chain. Well, let's try. We can try this. Now that I have this m, I can try bracket q and m. So this is a 1 chain. That's a 3 chain. So this thing is a 4 chain. But that's not what I want because it doesn't have any nice properties except, well, okay, so it's not the right thing, but I can do the following. I can check that this guy is actually 0. Right? Why? Well, because first of all, if you hit here, you're going to get the total charge, and all these guys are U1 invariant, so that's 0. If you hit m, you use, well, this m. Then use that thing, and by Jacobi it vanishes too. So this is 0, therefore, something like this, where n is, so there's a 4 chain, so it's a 5 chain, which also preserves omega and U1 invariant. And if it's a 5 chain, I can use it in 4-dimensional constructions. So I get a numerical invariant also for 4-dimensional systems. And you can iterate this and you get a 1 numerical invariant for every even, for every even dimensions, 2, 4, and so forth. Now, if you compare this with physical expectations, that's exactly where I expect something like whole conductance to appear. So in the field theory approach, you would say, well, if you have U1 symmetry, then you can measure sort of a response of a system to external field, and topological responses are given by Chern-Simons actions. And Chern-Simons actions exist for U1 exist in dimension, in space in dimension d+1 when d is even only. It's exactly 1, and for U1 group, there's exactly 1 parameter there. So actually, these are precisely should be identified with these Chern-Simons responses, and so you get all these Chern-Simons invariants, which are generalizations of whole conductance to higher dimensions. Moreover, you can actually do it for the nonabelian case, similar thing, and you just discover that similar constructions gives you invariants which live now not in numbers but in invariant polynomials on the Lie algebra of the group. And again, they occur only for even spatial dimensions, and again, those are precisely the same thing which gives rise to Chern-Simons actions. So it seems like you get the same, you get all invariants in the same way. All invariants expected on field theory grounds from topological field theory are recovered from this formalism. So that's part I'll just skip because it doesn't involve any new ideas.
So in the U1 case, the even dimensions are also where like cohomology or BU1
are
supported.
Yeah. So I'll get So there's actually something. Yeah. So you can also generalize this whole thing and relate it to equivariant cohomology of stuff. Yeah. Right. So in general, this invariant takes values in H d+2 equivariant cohomology of a point of degree d+2. So for U1, it's just polynomials of degree, the invariant polynomials on the Lie algebra of G of degree d+2/2. Could basically assign the Lie algebra sits in degree 2. So that's what. Okay. So it gives you precisely the kind of Chern-Simons coupling. Same group theory, it gives Chern-Simons couplings in dimension D, space in dimension d+1, and group G. But now we can sort of see the meaning of this whole conductance. For example, it's an abstraction to promoting your symmetry to a local symmetry in such a way that different sides still have commuting symmetries. So that's exactly what this M was abstraction to. Yeah. Where is it? Did I already raise it?
Could I just ask a question to make sure I'm understanding?
Yeah.
So I think I was confused earlier. It doesn't really matter that it's a lattice, right? It could just be any collection of relatively evenly spaced.
Yeah, I said that's called Delaunay set. Yeah.
Oh, okay,
Yeah. So we just assume that the points don't accumulate, so it just has a minimum distance between any points.
Are you going to discuss quantization?
Well, yeah, but first I will discuss Berry phase, Berry curvature, which is also not quantized yet, but it's interesting to reinterpret this thing as a special case of some modular construction which involves some equivariant cohomology of something rather than a point. So this is pure algebra, but you can also, well, after all, in my abstract for this lecture, as I mentioned, Berry classes, so I feel obliged to discuss them. So now, okay, so one thing we can do then is invariance of states with symmetries. Another thing we can do is invariance of families of states. And here I don't care about symmetry. I might add it. The two things can combine nicely. There's some parameter space and an action of a group, but I'm not going to explain that. I'm just going to say it maybe in the end. So invariance of families, or smooth families of gapped states. Again, in the invertible case, we have actual predictions for what we're supposed to get, but I'm going to do it in the gapped case. So the first thing, what is a smooth family of gapped states? That's not a very trivial thing to define. So here's a definition which I adopt, which is quite natural. Well, one of the most natural definition, I guess, physically, to say, well, suppose you have a state, family of states, some M, which lives in some manifold, some finite dimensional manifold, and this is a gapped ground state of some family of derivations. And which depends smoothly, these derivations depend smoothly on M. Okay. I can make sense of this because these derivations, they form a Frechet space. So there is a well-developed calculus in the functions in Frechet spaces, so it makes total sense to ask what the derivative of this function on the manifold with values in a Frechet vector space is, and demand this function to be continuous, and then take iterated derivatives and say demand it to be infinitely differentiable. That makes perfect sense. I don't take this viewpoint because it's a more convenient viewpoint. One can show that if you have a family in this sense, then you have another interesting property that different states in this family are all related by some nice automorphisms. So usually it's referred to as quasi-adiabatic evolution. So suppose you have some of this manifold M, and there's some path in this manifold. Then turns out I can find one parameter family of very nice automorphisms, which such that, say, this is say M0 and this is M1. So, and I suppose I have a path M such that gamma of 0 is M0, 1 is M1. Turns out whenever I have this situation, I can find so there is a family of Hamiltonians depending on parameter T. This lives on this. So this lives in. So this is a. So G is basically a function from here to to these UL derivations, which are smooth functions. So it's a smooth family of some sort of Hamiltonians, but not the ones for which this guy is a ground state, just some formal guy, which does what? Such that, I'll write in physical notation first, such that if you construct evolution operator from this tangent family of Hamiltonians, then I will have that omega at point m0 is, sorry, I'll have that omega point gamma t is simply omega gamma of 0 composed with alpha g of t. So this easy way to construct one state of another is by automorphism of the algebra. So they claim there's a smooth and nice family of automorphism which maps state here to state there. If you wish, state here is applying from state there by applying some automorphism. That happens whenever you have a smooth family of Hamiltonians for which each of these guys is along this path, for which, and so the each point on this path is a ground state of that smooth family of Hamiltonians. So this thing then is kind of like a connection on some trivial bundle, if you wish. So it's better to think of, well, on this path. So, and you can do it for any path, of course. So it's better, a nice definition of smooth family is then that you have some one form actually on the manifold with values in these guys, such that the family of states is parallel sort of with respect to this family of Hamiltonian. So this is, here's the definition then.
So you also call G Hamiltonian with G of t.
Yeah, just G of t is not, but not a Hamiltonian it's a one which we use to evolve stuff rather than to, like this. None of the states are ground states of this G, for example, for any t. You just think you use to evolve things.
Okay. So we don't care what is the ground state.
Yeah, we don't care. Yeah. So this is definition, my definition. So. So basically, it's like an equation of parallel transport. So, so maybe it looks maybe nice. So I can, basically move d through omega, but it's expensive to turn to this sort of covariant derivative. Right? Maybe it's better. So for any a here, so it's kind of like a connection or trivial bundle with fiber, this fiber, but the connection not an arbitrary connection. It's a connection which lives in this very special group of very special Lie algebra, namely in this one. Not arbitrary, automorphic, not arbitrary derivations, nice derivations. Okay? So there's notion of smoothness. So you have your state can be, there's some G like that. Okay, I can. It's convenient to introduce maybe some notation, other notation. Suppose A instead, or equivalently, let A be rather some function on M with values in almost local observables. Again, it's a Frechet space, so it's a well-defined notion. Smooth function. Then I would say that omega is like this, where dA is just a covariant derivative, if you wish. Okay. So that's how we usually define something. Like if I actually had a finite dimensional, like in zero-dimensional case, when I have a zero-dimensional, the system with dimension 0, it's a finite dimensional quantum mechanics. This would be simply the algebra of all observables, because their locality has no meaning. And this guy would be simply the algebra of traceless anti-sulfide joint matrices. And that will be simply the statement that it's just some connection, or general connection. In higher dimension, I need to actually say which, it's a nice local connection, if you wish. So, yeah, so in general, this would be just some conditions that, omega is just a smooth section of a dual bundle to the trivial bundle of observables. Okay. So, okay, so now suppose I have this family, smooth in this sense, and I want to attach to this family some invariants. Now, in zero-dimensional case, for finite-dimensional convex systems, there's something called Berry class, which is, in that case, you have this omega is just a family of projectors with one-dimensional image in some fixed Hilbert space. So you get a line bundle out of that and on the parameter space. And the line bundle has some Chern class, so that's your Berry class. So claim to any such family can attach a class in here, in the de Rham cohomology. Okay. So for d equals 0, just usual Berry class, it's cohomology class of the first-order class, basically of the, well, de Rham reduction of the first-order class of the Berry connection, but in higher dimensions, some higher dimensional thing. Now, again, it's a question whether this thing is quantized in some sense. For example, can you lift it to maybe integral cohomology? And we don't know how to do it in general. It's probably not even possible because, by the way, so in the equivariant case, you have something similar, right? You have this equivariant cohomology of a point. There's some common generalization when you have both the manifold and action of a group on the manifold in the system, some equivariant Berry class, of which this is a special case and this is a special case. Then you just have equivariant cohomology of M of degree d plus 2. So, so these are both special cases. We know that in general, whole conductance is not quantized. We expect it to be quantized for invertible systems. So we don't expect this to be quantized either in general. But for invertible systems, we can prove this is actually integral class. And we actually have a paper which came out like 3 weeks ago, which proves quantization for d equals 1, the first kind of non-trivial case with the class in H3 for invertible systems. Also, whole conductance is a bit easier case. Again, for d equals 2, but only in this situation, you can show that it's also quantized.
So what do you mean with quantized?
I mean, it's actually image of an integral class. Okay, so if you use periods, just integral. But more precisely, it lifts to an integral class. If you have torsion, you can also detect that. So let me just given the last 5 minutes, I'll just say how to construct this class. It's basically the same.
So you say that this d plus 2 dimensional Berry phase it's always integral without the g.
No, it's integral. I only know it's integral for invertible system in dimension 1. So for higher ones,
And what was invertible again in terms of this omega?
I'll discuss invertibility on Friday. Yeah, so it's a special property without which it's much stronger than being gapped. And you can lift things to integral things only with this strong property. So you can hope to lift it. I don't actually know how to lift it in general dimension.
Wait, there's lecture on Friday too? Or?
Sorry?
There's a lecture on Friday as well?
Yeah.
Oh, okay.
Right?
I'm not sure if it's this week or next week, but we can check.
Okay, check. Maybe it's on next, I don't remember. Some Friday.
For me, it's showing next Thursday.
Okay, next Thursday. Well, if you must be right then. So you're the one after all who organized it. Okay, so let me just say how to again. So there is a okay. So here we do the following. So okay, we have chain complex, the C lowercase, and now we can consider forms on M. We're using these chains. Okay. So we have now forms which take values in derivations, which we already have, right? This G was a one form but in derivations. But you can also have forms with values in one chains, in two chains, and so forth. So okay, so what do we have? Well, the starting point is, again, we have this G. But let's define some curly G. So this G, let's think about this. This G has total degree, well, what is it? So it's a one form, and it's also derivation, total degree is 1, right? Now let's keep it this total degree 1, but we can go to also have some, these guys say G n, the chain degree, and those guys are going to be of high degree, form degree 2 as well. So the point is that somehow this guy has a differential, but the differential d plus del. And this d has a cohomological gradient, increases the degree by 1. But this one decreases the degree by 1. So if you think about this, if you want to think of it in the same way, let's just sort of reinterpret this n as minus n. So chain degree is kind of the negative degree, right? So you want the difference of form degree and negative degree to be 1. Okay.
Until that was too quick. Can you repeat what is G, small g?
Yeah, so I'm just going to say, so this G is going to be live in forms of degree n plus 1 with values in chains of degree n. So the difference of the degree is always 1. Okay. So that guy, then this kind of like a connection of total degree 1. So, and this thing I also interpret as total degree 1 because it's 1 here, right? And I also flip the grading, so it's also 1 there. Before it was minus 1 because my degrees were like positive. So somehow this is positive. This takes place. I can sort of reinterpret this. Interpret it as a minus something, right? So, and then I can write the following thing. I can write the equation which says the following. Let's call this, I don't know, curly d. So sort of more Cartan equation. Which says, another way to say that, that the curvature of this generalized connection, which has forms of arbitrary degree and chains of arbitrary degree, is 0. So, no, this by itself has non-zero curvature in general. But I want to correct it somehow by a higher form guy so that the whole thing is non-zero. And in particular, somewhere down the line, I'm going to have a chain of degree equal to d plus 1. So I'm going to have some guy there, g d plus 1, which lives in omega d plus 2, c d plus 1. And I know what to do with that. I'm going to integrate it and take average. So first question is, why can I even solve this equation? You can check that.
This integral is over m. It's not this integral of chains.
No, it's just integral over these regions
Okay.
a d plus 1. So this guy lives where? Well, after integrate, I got an observable, which is also a form of degree d plus 2. And after I averaged, I'm going to get just an ordinary form. Well, purely imaginary because everything's anti-self-adjoint. And then, well, first question, why can you solve this equation? Solution is always, it's very easy because when you solve this order by order in this n, and you always have an equation like this, you have del of something equals some expression, which you can check is from the previous g's, which is closed, del closed. So you can always solve it because everything that's, right, so you have always something like this. So you can always solve it because this guy, because it's explicit, you can something which everything which is closed is also exact. So okay, you can solve it, and then you can check that from this equation, this is called Moore-Cartan equation. Typically, this is actually closed. So not only it's actually closed form. So you get actually a well-defined cohomology class of degree d plus 2. And moreover, you can check that even though lots of ambiguity in this, how you solve this equation, lots of ambiguity. You can check that the cohomology class doesn't depend on any of this. Just depends on the family of the system you started with. So that's the procedure. Okay. That gives you this high Berry class. So in the last lecture, I'll just discuss we'll discuss quantization first of all, which you only know how to do in low dimensions, and also I'm going to finally define what it means by a phase. So what is a phase of matter? So which is not going to be very difficult given what we already know. Okay. So all this invariance, actually invariance of phases, homotopy invariance.
Can I just ask a question? When is the next lecture? So
I'm sorry. I think I said Thursday, but I think it was actually meant to be Wednesday.
Okay.
Wednesday,
Next
June
one.
7th.
Okay.
It's exactly 1 week from.
Okay.
Why more Cartana and why you took it a bit out of?
That I leave as an exercise because I don't know my answer myself. It's just something which works.
So it's just a machine which produces for you the
Yes.
forms.
And there's no guarantee that there is no like generalization which produces more invariance. And in fact, as I mentioned, I cannot produce invariance, say, of just isolated systems. So I'm definitely missing some invariance. Like if you just look at system without symmetries, no families. In 2 dimensions, there should be some new other invariants already in 2 dimensions, but I don't know how to make them. Since I don't understand this guy, I also don't understand why it comes about. I don't understand what is the most general thing you can extract out of this complex.
In 2 dimensions, be more variance because of the thing you said in the first lecture. You expect
Yeah, you expect some. Yeah, well, no, this is Z factor. Like there should be some integer varied invariant for invertible phases, and more generally for gapped ones should be some real number varied invariant or rational number varied invariant. So I don't know how to make it, but maybe because I'm not smart enough to figure out how to use this machine of this DG Lie algebra.
So in this case, what is the assumption of being gapped enter?
A cyclicity, this Lie algebra of symmetries
Being a cyclic.
is a cyclic. That's what what enters. It's what enables you to solve this equation. Yeah. So I forgot to say it's not just C. Sorry, that was bad. Yeah, so it should be C with a subscript omega superscript. For C, it doesn't give you anything interesting because you cannot prove that this thing is closed with C, right? With C, you just have some purely kinematic thing and you don't know what to do with them. It's supposed to, if it's just averaged over some unrelated state omega, that doesn't have any special properties. But if you have average in omega, it's actually going to be. If,
C also a cyclic?
yes, but then what do you do with the? You can still solve this equation, get something, but then it depends on lots of choices. And what do you do with it? Well, you need to average it maybe or something, but your construction must somehow connect to the averaging procedure, right? So the averaging procedure works and gives you something interesting only when you solve within this complex. And that's, by the way, why we work with this class of Hamiltonians, because if I say you work with finite range Hamiltonians and all my chains would like just terminate at some range, which is what coarse homology people do, then I would not be able to prove a cyclicity and I wouldn't be able to solve anything. So we're sort of forced to work with this particular class of chains by the desire to solve this equation.